Now we come towards the physical significance of the moment of inertia. The physical significance, how it is applicable to the material bodies. The physical significance of the moment of inertia assumes that moment of inertia I plays the same role in rotational motion as mass plays in linear motion. This I have discussed earlier. So I is again inertia for the rotational body and m is the inertia for a linear body. A body free to rotate about an axis has a tendency to oppose any change in its state of rest or the state of uniform rotation. The body opposes any torque or movement of couple that tends to change its state of uniform rotation. Like a body is said to be in rest if it does not change its position with respect to surroundings. But if a body changes its position with respect to surroundings, it means it is in motion. The same concept has been applied here in the physical significance of the moment of inertia. Thus, the body has inertia for the rotational motion. The nature of rotational inertia must be that of movement. Hence, the name moment of inertia. Greater the moment of inertia of the body, the difficult will be for force to change the state of rotation. If the whole mass is concentrated at the center of mass, then it is very difficult to, by the force, to change the state of rotation. So, moment of inertia of a body can be regarded as the measure of the rotational inertia of the body. The unit of moment of inertia, that is I, that is mr square. M will be in kilograms and r square, that will be in meter square. R is distance. So that's why the net dimension, that is T is not existing, that is M1 L2 T naught, M1 L2 T naught. Such a quantity in which T has an index of 0, that is called a tensor quantity. So what is a tensor quantity? In which the dimension of T is absent, not existing. Moment of inertia, the rotational motion of an object. Now it is shown in the figure. R1, R2, R3 are the radii for the same masses, where M, so it means that V1 will be like V1 is R omega, so we can write R1 omega, V2 will be R2 omega, and V3 will be R3 omega. And axis of rotation is indicated, and it is shown the top omega as the axis of rotation. Now we come toward the radius of gyration, which is quite comparable to the torque. The radius of gyration of a body about a given axis is the perpendicular distance of a point P from the axis. Where if the whole mass of the body is concentrated, the body shall have the same moment of inertia. So if the mass is concentrated at the center, the moment of inertia of all the points will be same, as it has with the actual distribution of the mass. Now this distance is represented by K. Now for n particles of equal masses at R1, R2, R3 from the axis of rotation respectively. So when we find moment of inertia, it will become m into, that is R1 square plus R2 square plus R3 square up to Rn square, that is up to n particles divided by n. So it is mr square by n, or I is equal to mk square. M is as it is, and for k we have computed R1 square plus R2 square plus Rn square divided by number of particles. The dimension of the radius of gyration, if we want to find the dimension, the k has the same dimension as of length, so the dimensions are written as m naught L T naught. The value of radius of gyration shall depend upon the shape and size of the body, the position and configuration of the axis of rotation, and also on the distribution of mass of the body with respect to the axis of rotation. Now, Again, torque and moment of inertia. So as we have discussed earlier about torque, that is the force into perpendicular distance, and moment of inertia, that is moment of inertia is I, that is mr square. So we have to now relate torque and the moment of inertia. Now torque is taken as I alpha, where I is the moment of inertia of the body about the given axis of rotation. This equation is known as the fundamental equation of the rotation or the law of rotation. So law of rotation is given in terms of moment of inertia, the product of moment of inertia with alpha, that gives the value of torque. Now angular momentum and moment of inertia, that is for some typical rigid bodies. A rigid body, again and again we are choosing, and rigid body means a body which has plenty of particles, those particles in the form of atoms, and all these particles or atoms are arranged in three-dimensional repeated pattern in the whole body. Now, V1 is R1 omega, V2 is R2 omega, V3 is R3 omega. This we have discussed earlier also, and we are again repeating it. So, angular velocity omega is the same for all the particles about the axis. Therefore, the linear momentum of this particle about the given axis will be the product of mass and velocity. So, P1 will be m1 v1, and we have written m1 as it is, and v1 is written as r1 omega. That is, earlier we have taken the linear velocity, and r1 omega is the angular velocity. The angular momentum of this particle about the given axis. Angular momentum is momentum into radius of rotation. So momentum is written as m1 and r1 omega multiplied by r1. And the net expression will become m1 r1 square omega. Similarly, for other particles, we have the same rule. So net angular momentum is taken as summation of all these numbers, that is m1 r1 square omega, then m2 r2 square omega, then it is m3 r3 square omega up to the nth particle, that is mn rn square omega. Everywhere omega can be replaced by v over r. So angular momentums, omega is taken out common and remaining values are written in the brackets. Now L is equal to I omega, where I is the moment of inertia and omega is the angular velocity. So omega can be replaced by V over R and I can be replaced by mr square. So if we make the cancellation, L can be written as mvr. This angular momentum of a body about the axis of rotation is given as the product of the moment of inertia and the angular velocity of the body about that axis. Now, if we differentiate the above equation with respect to time, we can write dl over dt is equal to d over dt I omega. So this is what written here in the equation. So I is written as it is, L is written as d omega by dt, and d omega by dt is taken as alpha. So the torque is I alpha. So dl over dt is I alpha, but I alpha is torque. So dl by dt is basically torque. So torque is the rate of change of angular momentum with respect to time. Therefore, dl by dt is 0. Torque acting on a body is measured with the rate of change of angular momentum of body when no external torque acts on the body. And this is mathematically taken as torque tau is equal to 0 into dl by dt. The net expression will be 0 and L will be constant. This is the principle of conservation of angular momentum. Now we have to go through with a comparison of the linear and rotational motions. Like in the linear motion, there are three general equations like V is equal to U plus AT, S is equal to UT plus half AT square, and 2AS is equal to V square minus U square. But in rotational motion, the velocities will be changed by R omega. So now in the linear motion, distance or displacement is s, but in rotational motion, angle or angular displacement will be theta. That is, we talk in terms of angle. Then linear velocity is v, that is derivative of displacement with respect to time, that is ds by dt. But angular velocity is represented by omega, and that is derivative of angular displacement with theta. That is s in rotational motion is replaced by theta. So we have taken earlier ds over dt, but now we are taking d theta over dt. The third important point is that linear acceleration is alpha, and that is rate of change of velocity, that is dv by dt, or it is d square s over dt square. And in case of rotational motion, instead of taking linear acceleration, we have to take angular acceleration. That is alpha is equal to d theta over dt, or d square theta over dt square. As earlier we have taken d square s over dt square. Now the mass, when we come to mass in the linear motion, that is m stands for mass, and the body has got mass, inertia. But in rotational motion, we don't simply say mass, but we say moment of inertia, and moment of inertia I must be mr square. And then comes the linear momentum, that is straight line motion, and momentum is the product of mass and velocity. Whereas in angular momentum, L is equal to I omega. We can use angular momentum in the Bohr's atomic model as well as in the Sommerfield's atomic model. Now, next is the force F, that is m into A. Here the torque will be not m into A, rather it will be I into alpha. So we can remember here, alpha is rather more important. And next is the seventh point, that is, we will say that the force is rate of change of momentum, that is derivative of P with respect to T. And the torque will be derivative of L with respect to T. Now, in the eighth case, it is translational kinetic energy, which is half mv square, but rotational kinetic energy is half I omega square. Now, in the linear work done, it is F into S, but the angular displacement, the work done will be torque into theta. Now, power in the linear motion is the product of force and velocity, but in case of rotational motion, the power is the product of tau and theta, that is torque and theta. Now, in case of linear momentum, when no external force is acting, the momentum is conserved. That is called principle of the conservation of momentum. Similarly, angular momentum of system is conserved when no external force acts on the system, and that is called the principle of conservation of angular momentum. Now, on the left portion, the 12th part, we are taking general equations of the accelerated motion, that is uniformly accelerated motion. U plus at, then it is ut plus half at square. U is initial velocity, a is acceleration, and t is the time in which velocity is changing. The third equation is v square minus u square is equal to 2as, and these symbols have their usual meaning. But in the rotational motion, omega square will be equal to, or omega 2 will be omega 1 plus alpha t. Omega 1 is comparable to u, and omega 2 is comparable to v. Similarly, S is equal to ut plus half at square, but in rotational motion, S will be taken as 0. So it will be taken as omega 1t plus half of alpha t square. And same is the case for the third equation, that is omega 2 square minus omega 1 square is equal to 2 alpha into 0.